frequency response for parallel load. With the load connected across the capacitor C through a transformer or directly in a parallel loaded circuit, here we have a equivalent circuit. Then using the voltage divider rule, the frequency domain, the voltage gain is given by J omega equals to V naught by Vi of J omega, which equals to 1 by 1 minus omega square LC plus J omega L by R. Now, omega naught equals to 1 by square root of LC is the resonant frequency, and Q equals to the quality factor 1 by Qs, where Qs is the quality factor of the series loaded, which equals to R by omega naught L. Now substituting the LC and R terms for quality Q and the resonant frequency omega naught, we are going to get J omega equals to V naught by Vi J omega terms, which equals to 1 by 1 minus omega by omega naught whole square plus J of omega by omega naught divided by Q, which equals to 1 by 1 minus U square plus Ju by Q, where we know that U equals to omega by omega naught. Then the magnitude J omega is given by 1 by 1 minus U square whole square plus U by Q square under the square root. The frequency response is as shown in the figure, where the magnitude plot of the voltage gain for Q equals to 1 to 5 is as shown. The maximum gain occurs near the resonance for Q is greater than 2 and its value for U equals to 1. Then for this, if U equals to 1, the magnitude J omega equals to 1 minus 1 whole square 1 by Q square under the square root, which is nothing but 1 by Q, which equals to Q. So at no load, if R equals to infinity and this Q equals to infinity. Thus, the output voltage at response is a function of the load and can be very high at no load if the operating frequency is not raised, but the output voltage is normally controlled at a no load by varying the frequency above the resonance. The current carried by the switching devices is independent to the load but increases with the DC input voltage. Thus, the condition loss remains relatively constant, resulting in poor efficiency at the light loads. If the capacitor is shorted due to the fault in the load, the current is limited by the inductor L. This type of inverters is naturally short circuit proof and desirable for the applications with severe short circuit requirements. This inverter is mostly used in low voltage, high current applications where the input voltage range is relatively narrow, typically up to plus or minus 15%.